So our duct systems in our homes are going to make or break how energy efficient, healthy, comfortable, and how long our heating and cooling systems last, especially as we make the transition to heat pump technology, air source heat pump technology. And so it's very important that we take a look at all of our existing homes, single family, multifamily, that are using duct distribution systems to look at the effectiveness of those and make sure that those are improved to deliver the sustainable outcomes we want to achieve. And in our new construction, it's still not getting done correct. And we need to make sure that there's a lot more thought going into the ductwork distribution systems that are being put into our new housing standards. And so that's why I am super excited to be having this discussion here today, and I hope you will join us. Now, before we get started, a huge thanks to one of our top tier platinum sponsors, Rheem. So, a little bit next to the duct system, of course, is our water heaters, and we can easily decarbonize those if we want to have the bigger systems that have that sort of backup resistance heating in them. Rheem has its 240 volt systems, which might require electrical upgrades in existing homes, but they're going to have that backup resistance heater there for times of high demand. Otherwise, you have your plug and play 120 volt systems through Rheem that just plug into a standard outlet, don't require the electrical upgrades. And so that's going to be another way to do that. And so both of these are super high efficiency, near 400%. Plug it right in, take the heat out of the air. I've been using it since 2018. I've got a relative using the 120 volt version. Great system to help decarbonize and reduce energy bills and be healthier. So check them out over at greenhomeinstitute.org/REAMHPWH. All right, welcome to Duct Diagnostics, evaluation and troubleshooting for real world systems. This session is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We are a small but mighty team here, and today I will be your moderator. My name is Brett Little, and I am the education manager here. As always, this session, like many of our sessions, is approved for multiple continuing education units, including 3 of the 5 pillars of green, energy, health, and materials. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Check out that 5-digit passive house code that will be sent to you in your certificate as long as you're here the entire CEU approved hour. Now, one thing we're looking at is trying to see how these improvements, both in home improvement and new construction, work if you're using the LEED green building system. So we're going to be talking about the basics, the understanding of how we do this, and if you're incorporating it in LEED, where can you get your points to do that? And so that is within LEED version 4.1, the residential system, under indoor environmental quality EQ, balancing of the heating and cooling distribution system. You can find the information about all of that on the LEED credit library. And so what we're looking at here is the intention of getting credits in this section to follow these guidelines to improve that thermal comfort and energy performance by ensuring appropriate distribution of space, heating, cooling system within homes. And so we're not going to talk about all of these today, but a couple we're going to hone in on a little bit here today is the 1 point we can get for supply airflow testing, which is very important to repair our existing systems towards, and especially to get right in our new construction systems. And so 3 key things you need to know about this that we're going to go into much more detail is that first, we're looking to get within 10% of the installer's measured air fan flow, which comes on the specs of the system, or 15% of the design HVAC air fan flow, which is usually under the Energy Star for Homes program for LEED. And so we're going to get into these details, but you can also get a bonus point if you're within 20% or plus or minus 20 CFM flow rates if you're using the ACA standard for the quality installation specifications or the ResNet 310 standard if your rater is doing that verification. Also, you can just throw all that out and do a ducted mini split or a ductless mini split. If it's ducted, it's got to be less than 10 feet of ductwork. And then you don't have to worry about all this stuff. there is no concern there. So you can use that pathway. Of course, when you do, that's going to be one of the components that leads to good static pressure. So it's not a drag on the health and performance of your system. And that might allow you to have a bigger MERV filter, which gets you more lead points and has a healthier home. So what you're trying to do with static pressures, you're trying to make sure that you're within one IWC, and we'll go into that, of the Energy Star for Homes design HVAC checklist of what we're trying to achieve. And again, that's supply and balancing, airflow testing. That's going to help get you to this. Now, when you do all of that correctly, another thing you're going to have, hopefully, is a quieter system, because loud systems can really drag on people's health and comfort by being too noisy. And so for lead, we can get an extra bonus point if we go in and test homes. And you want to do this for any home, lead or not. Is the system quiet? Is it too loud? Because a loud system is a sign of a problem. And so we're going to be able to do that testing, get that extra point, and we'll talk about, again, how getting how this kind of all connects to have a better performing system. And finally, let's control it with a better thermostat, a smarter thermostat, a remote access thermostat, and even from a lead standpoint, you can get a bonus point if that is an Energy Star thermostat. And there's other components of thermostats outside of this that you want to consider for controlling that system. So enough about that. We're going to get into the details of how to do all of these things with our speaker here today, Bryn Cooksey Sr. Bryn has been on the show once before, and Bryn is also a board of member director at our organization, and he is the chair of our technical advisory committee. So, Bryn, it's good to have you back on the show. Welcome back, and please go ahead and take it away.
All right, thank you, Brett. We will get started here. And Brett, can you see my screen okay?
It is loading. There it is. Yep.
Let me just get you guys out the way. All right, perfect. Hello, everybody. My name is Brent Cooksey, owner and founder of Air Doctors Heating and Cooling. We're a home performance contracting business based out of Southeast Michigan. And we have a technical training organization, a sister company called HVACU. Most of my time is spent doing training and presentations like this. Today, we got a really important topic. We're talking about duct diagnostics. I give you a kind of a introduction of why this is so important. And Brett mentioned it during his introduction. And about, I'll say 2021, the year 2021, we were coming out of COVID. And our business, we were personally into about 3,880 homes. And in those homes, we wanted to see, was the myth as bad as we heard, where equipment was grossly oversized and the ducts were grossly undersized. So we tracked that, and we found out that 99% of the houses that we were in, and they range from ages from really old homes built in the early 1900s all the way into 2020 when houses were finished, those houses all had duct systems that were about half the size that they needed to be. And that same survey that we did, we talked to many customers, and even these new houses, they had house rooms inside their house where they were uncomfortable. They couldn't occupy because it was either really hot in the summertime or really cold. So in this presentation today, we're going to talk about how to evaluate the duct system so you can make changes. And as Brett mentioned during his introduction, it's still a problem in new construction. I have some new construction houses built as early as last year that we had to modify the ducts. So let's get going. In this presentation, we're going to talk about the components that make up the four-tier system. We're going to talk about common diagnostic assessments, and then we're going to talk about common problems and then solutions. All right. Now, when we look at a duct system, let's talk about its purpose. Its purpose is to provide conditioned air to all the rooms. All right. If you look at Manuel J says a good ducted design should keep the rooms between less than 3 degrees Fahrenheit. All right. So we want them to be thermally even. All right. We want those rooms to be comfortable. Brett mentioned static pressure. We need to make sure that our static pressure is modest and within specifications. We also want to make sure the ducts are sealed. A leaking duct system can cause some issues with the building pressures inside. We'll talk about that. And we want balanced supply and return. When we design a duct system, we design it so that if we're delivering a CFM to a room, we want the same CFM to return, except bathrooms and kitchens. So we'll discuss that. And we want insulation on our ducts if they're unconditioned spaces. All right, so these are all common things that we run into with duct systems. Now, when we look at the duct system, the parts include the air handler. All right, in this case, we're in Michigan, Southeast Michigan, so we have a lot of furnaces. So to get our terminology correct, a furnace is an air handler with burners. All right, so you're going to hear me use those interchangeably. The start of the process is from the blower inside the system. All right, it's going to push air through that heat exchanger, if it's a furnace or a heat exchanger on the air conditioning side. It's going to push that air through a duct system. That duct system is going to terminate in rooms. That air is going to blend with room air temperature. Then it's going to come back to the return and start the process all over again. All right, highly technical. And the reason why this presentation is important, if I don't get the ducts right, I can never get the energy out of the air handler or air conditioning system. If I have a 3-ton system and the ducts are undersized, it won't deliver 3 tons. So super important. All right, what you see here is a duct system, and this duct system is common what we see in the Midwest. In the Midwest, we have basement applications. And what I want you to see here is that the duct system is quite intricate. When we're looking at this duct system, we see that we have various shapes and sizes. All right, these shapes and sizes are often done to accommodate some building construction. So you see how this is right here, kind of oddly shaped. It's flat. All right, that's a wall stack. So the duct system, the fittings that are designed and spec when a new duct system come in, are really designed to help accommodate building construction. All right, they all have pressure drops and all that kind of stuff. We need to understand when the duct systems go in. But as a trainer for about 20 years, duct design and duct evaluation is really not a well-developed skill, and that's just my opinion. All right, another thing that we look at that we don't see when we look at duct systems are balancing dampers. All right, was the system balanced? All right, oftentimes it's not. So we're going to talk about that. Now, what are the consequences of poor airflow? All right, if we don't have adequate airflow, we can't get the energy either into or out of the equipment. All right, it causes poor comfort. All right, we're going to have areas of the building or our house or the system itself where we don't have adequate temperatures. All right, and maybe the reaction from the customer or homeowner is to turn the thermostat up or down to kind of alleviate that. All right, so it's going to cause longer running times. Those longer run times are going to contribute to higher energy bills. All right, what happens when you have a unreconciled duct system to equipment, you're going to have the situation where customers are going to be uncomfortable. They're going to respond to take action. And when they respond to take action, it's actually going to make the problem worse, not better. So we're going to talk about that. In extreme cases, we can get frost buildup on the evaporator coil. If we're in the air conditioning mode, and we can flood back to the compressor, we can damage that, and we can shorten the life of those components. And oftentimes, in the heating mode, we run into cracked heat exchangers. Right? This is a picture where a technician cut a hole inside the return air to alleviate some high temperature limit problems. And when we look at the house as a system, all right, this return air, which was trying to relieve the furnace from short cycling off on a temperature limit, was actually overcoming the exhaust gases and the flue piping. All right, so it's highly important that the ducts not only be done for efficiency purposes and comfort, but if we do a mistake like this, it can also be harmful to the occupants. All right, looking at our distribution system. So we're going to start at the blower is a point of pressure where we're going to increase the pressure, circulate the air through the duct system. And the air handler or furnace, or if we have an attached air conditioning system or heat pump, we're going to have a series of heat exchangers. All right, depending on your mode, that air is going to travel across those heat exchangers and go into the distribution system. Now, the point of the duct system is to get the air from point A to point B really quick without a large pressure drop or temperature losses to get it to point A to point B really quick. So we don't have the duct system sized properly or balanced, or if we have errors like not duct sealing or insulation problems, we're not going to achieve those goals. Right? Function of the heat exchanger. The heat exchangers are in the air path of the distribution system, and they're going to take that energy either out of the airstream or they're going to put energy into it. Now, this is where a lot of the work is done, and if we don't have proper airflow, we can start to set up these heat exchangers for failure. All right, here's an example. This is the actual heat exchanger failure, where if I have a furnace that is underducted, it's going to short cycle. And what happens when furnaces short cycle, the metal inside the heat exchanger starts to anneal. If you think about when you were a kid, maybe you had a piece of plastic and you bend it back and forth several times. What happened? The plastic eventually was broken. That's what happens when you have a duct system. All right. The air can't leave the furnace bonnet efficiently enough, and it's going to short cycle, oftentimes on high temperature limit. And what's happening to that metal, it heats up and cools off, it's annealing and eventually it's going to break. And when we break, we get a situation like this. Now, what's bad with a crack heat exchanger? A crack heat exchanger represents that I have exhaust gases, which were not designed to breathe, mixing in with the air inside people space, right? So pretty hazardous situation. And in some cases, it comes from a unreconciled equipment to duct system. The ducts are too small, right? What about ductwork efficiency? We mentioned that we want the ductwork to get our air, conditioned air from point A to point B. It needs to do it quickly, all right? So it's a couple of things we need to look at. One, are the ducts sealed? Now, here's the thing. In order for ducts to be sealed, they should be properly sized. And we properly size our ducts by using industry standards like ACUS Manual D. When we do a Manual D and the ducts are sized appropriately, then we can seal the seams. When we look at the seams of ductwork, oftentimes in older construction homes, those seams were not sealed. AeroSeal did a study on this a long time ago, maybe some 20 years ago, and it's an average between 20 and 40% loss from your supply to the system, to the rest of your system, your ductwork. So you're losing on average roughly 30% if your ducts are not sealed. All right, so you need to design them first with ACUM D, and then they need to be sealed. However, if you seal ducts that were not designed properly, you're going to make the problem worse as far as static pressure, like Brett mentioned earlier, and you're going to damage equipment. So ducts have to be sized, and then they have to be sealed in all cases. All right. Now, what about ducts outside the thermal pressure boundary, outside our building envelope? How should we handle those? If those outside areas are vented to atmospheric pressure, such as a vented attic or crawl space, we need to not only size them appropriately and make sure they're sealed, but we also need to insulate them. They need to be insulated. All right. Not having ducts insulated causes another issue. When ducts are not insulated, they reduce our system capacity and they increase our load. All right. So something to think about. Think about the ducts. All right. Here's some duct sealing. All right. This is in the basement. A joke we use here at Air Doctors. Duct tape isn't for duct work. All right, we got to find an approved way to seal the ducts. Now, notice how this duct system in these two images here, they're not insulated. The reason why, they're in a thermal pressure boundary. Yes, they're probably in cooler locations like a basement, and you can argue that maybe they can be insulated, but in all intent and purposes, if they're inside the thermal pressure boundary, then it's not cost effective to insulate the ductwork. Would it help from a comfort standpoint? Absolutely. Now, when we look at the duct controls, let's talk about the duct system controls. Let's go start with the thermostat. Thermostats are really sophisticated nowadays. We have thermostats that can do everything. They can communicate with us. They can, I know my thermostat personally, as I'm heading home, it geofences my location. It would actually tell my system to start working before I get there so that I'm comfortable. All right, technology we really didn't have 20 years ago. All right, so the thermostat is a user operated control. And like I said, there's many options out there now. The second control that maybe is not understood by many auditors is that the furnace has some type of limit, all right, some type of limit control. On older equipment, it was a fanning limit. Now it is the limit. All right, what does the limit do? We'll talk about that. What about balancing dampers? They're really important to have those. Oftentimes we don't see them. And then in some cases, we've solved comfort problems by modifying the duct with motorized dampers. Let's explain. All right, we talked about the thermostat, user operated control. Pretty much the way your system works is going to react to a set point and it's going to run until the set point is satisfied. That's how your thermostat works. They have a lot of features, a lot of interconnectivity. They can be connected to other items in your home, such as a smart house, but this is the decision maker that tells the system to turn on and off. Okay. And what happens, we if we don't have a good equipment size to duct process, customers see that they may have a thermostat that's satisfied, but they still may feel uncomfortable due to other factors. So the reaction is they may want to go and alter that thermostat. Right? This brings up our limit control or fan limit control. On older systems, we had a fan limit control where this control controlled the fan function on the furnace and the limit. Newer furnaces now have an integrated circuit board that controls the fan function, but they still have this limit. All right, what does this limit do? Duct undersizing is so prevalent, manufacturers take action to actually protect the equipment from overheating. What we call it a limit control. All right, typically it's set around 200 degrees Fahrenheit or so, it depends on the manufacturer. And what this does, if I can't circulate enough airflow to keep that bonnet cool, this limit shuts the equipment off. All right, shuts it off. So this is the limit control. Let's talk about balancing dampers. Really, unfortunately, when it comes to ductwork, this is often what I see that's never done. All right, what is balancing? Balancing was the process of after I designed my system with a load calc and I came up with a specific BTUs and CFM for rooms, I would design a duct system to deliver the CFM to those rooms. When I design my CFM to go to those rooms, I need to commission it. So I need to take a device, maybe a flow hood, and I need to verify that I have the CFM coming out of the ductwork that I designed for. All right. And we call that commissioning or balancing. Now, in order to balance it, we need dampers. We need balancing dampers. So this balancing damper is a damper piece of metal that goes into our duct distribution system. And typically this goes into the branches. And its purpose is oftentimes there is a difference in CFM requirement between heating and cooling. In Michigan, we are predominantly a heating where I'm located here, and we have a different BT requirement for cooling. All right, so those airflows often are mismatched. The way you size duct systems, you have to size it for the worst case. And when we size it for the worst case, we have to use a damper to correct the airflow for the other case. So we have to do balancing. When we do balancing, we're going to test it in a heating mode and cooling mode. And then we identify on the dampers the position of that airflow where it's going to be marked at. All right, guess what? You can't balance a system if it's not properly sized. All right, you can't, the duct system, if it's not properly sized. And you can't size a duct system if you don't have a load count done. So oftentimes, balancing is a step that's skipped, and we can correct a lot of things if everything else is in order. Now, one thing that we've done to help customers is to, in addition to balancing, go with zoning. Zoning is a way to satisfy some uncomfortable areas. This is my favorite solution when I'm dealing with a home that's maybe 2 stories. I have a large home, and let's say I got one system servicing that home and it's located in the basement. What happens on the first floor, even if the ducts are sized correctly, the thermostat is on the first floor and it satisfies way before the airflow can get up and satisfy the second floor. So what we do with a motorized system, we're going to put dampers in all the branches and we're going to separate them. Oftentimes what we do, we put the duct runs that are going on the second floor, we put them on a zone, and the duct runs going on the first floor, we put them on a zone. And then we use 2 thermostats and we offset those. And when we offset them and the ductwork is sized appropriately, we can deliver conditioned air just to the zone it's calling. When done effectively, studies have shown that this has been able to save about 10% of energy savings. All right, that's motorized dampers. All right, so now let's talk about some common ductwork problems. All right, we have duct leakage to outdoors or duct leakage in general. We have a restricted return side. The system wasn't balanced, what we just talked about. We can have improper temperature rise, too high or too low, static pressure, something that Brett mentioned. And we're also going to look at the air handler flow not match the system. And lastly, we're going to talk about people living outside the distribution system. All right, we'll talk about that. All right. When we go to talk about those issues, these are the solutions that we're going to use to find the problems. All right. So in order to find the problems that we just mentioned, we're going to talk about these diagnostic tests. All right. So we have a pressure pan, a duct blower test or duct leakage tester, static pressure, temperature rise, room to room pressure differentials, and then measuring air handler flow. All right. So these are the 6 tests that you can use day in and day out to solve any kind of duct problem. It's going to get you right into what's going on with that duct system. All right. So let's talk about duct leakage. All right, duct leakage is a big deal, especially in this country. Aerial seal, again, 20 to 40%. We're going to call it 30. All right. When we have duct leakage, and let's look at it from inside the thermal pressure boundary, duct leakage is still an energy penalty. If I leak 30% of my conditioned air, it's going to take me longer to satisfy the thermostat. Hence, I have to use more energy to satisfy. So that's an energy penalty. Some people say that the leakage still happens in the thermal pressure boundary, but I don't control where the air goes. And as a result, I still have some issues. So if it's in a thermal pressure boundary, it's still an energy boundary, it's still an issue. Now, where it really gets bad is when it's in an unconditioned space. When you leak ducts, either supply or return, you're bringing in or delivering air into that unconditioned area. And if you lose that conditioned air to that unconditioned space, that energy is gone. All right, you're going to have to pay your utility to recondition the air to replenish what was left, what was taken out of the house. All right, so duct systems that leak reduce system efficiency. They can also cause some comfort issues. All right, and then lastly, they can cause building shell imbalances. We'll talk about that. All right. If we look at the return side, is even more diabolical. It's pulling in air from unconditioned space. So we have a vented attic or crawl space. It's going to bring in that unconditioned air into the duct system. It's going to increase our load and it's going to decrease our capacity. However, air from an attic or crawl space often isn't the best place to get air from. Well, why is that? What's in the air inside an attic or crawl space? We have rodent activity, possibly, maybe mold spores or fiberglass fibers, any host of indoor air quality issues that can cause some type of respiratory ailment. All right, so if we have air leak on the return side, we have the same problems and it can cause some IQ issues. In addition to that, we can also trigger our building shell related problems and even have problems with our combustion appliances. Okay. What about system wide consequences? How does a lack of airflow help that? It contributes to high utility bills, right? The airflow not being delivered to the space is an energy penalty because my equipment has to run longer. All right. If the equipment short cycles, that's a big problem too. A lot of people don't consider that the duct system, when it's not working properly, especially when it's due to an oversized piece of equipment, that if the equipment short cycles, equipment is rated in cycles. So if it short cycles really often, I'm going to get a mechanical failure a lot quicker than that part was designed for. I get poor humidity control. All right, I can again affect my building shell pressures, and I won't meet my program standards. All right, like lead. All right, let's talk about one test. This is a pressure pan test. All right, pressure pan is a calibrated, I call it a piece of plastic with a hole in it. And what it's doing, it's able to capture pressure differences across a surface. All right, the way the pressure pan works, I can pressure pan a register or grill. And this is especially useful when a duct system is in an unconditioned space. If I pressure pan that register or grill while the blower door is running, using a reference point of 50 pascals, I can then see if the duct system is leaking and communicating with the building shell. The duct system, if designed right, being properly sized and sealed, it should be at the same pressure as a house. So I really shouldn't get a large pressure difference. However, if it is leaking, it's connected some portions outside. When I run a blower door test, I will see a difference. All right. So the duct pressure pan test, when I take that pressure pan and I go across a register or grill, helps me to know that the ducts are communicating through the building shell. All right, again, this has to be done with the blower door running. We're using a blower door to maintain that 50 pascals test pressure. And what we're doing, we're using that reference pressure to see if there is any kind of measurable leakage across that duct system. All right, and what you're going to do, you're going to test each register and document the readings. Since this is a pressure test, if you have registers that are too large or oddly shaped, you can cover them with tape or plastic and get your reading that way. And how you fix it, you're going to seal the ducts and you're going to reperform the test. Okay. And the goal is to have pretty close to zero. I want less than one. Anything over one is really unacceptable leakage. You're having leakage, conditioned air leak out of the thermal pressure boundary. Again, that is a bigger energy penalty. All right. Another way to evaluate for leakage. Now, how does this differ? The pressure pan test is measuring the pressure differential across the thermal boundary. It's really looking to see if the ducts are communicating with the space, all right, unacceptably with the space and outside. This is a different test for a different purpose. It still is going to evaluate duct leakage, but now we're trying to quantify duct leakage. Quantify, actually get a number. All right, so we have two tests that we do to quantify duct leakage, and one is total duct leakage, where we're looking to see how many CFM are we losing if we have a reference point? And then the other one is going to be duct leakage to outdoors. All right, duct leakage to outdoors is another problem that we have to deal with because it's a bigger energy penalty. When we do total duct leakage tests, all right, we're going to either pressurize or depressurize the duct system using a duct leakage tester. And the test pressure reference here is 25 pascals. All right. And what we want to do, we want to measure the system and we're looking for it to be less than 10%. Now, this number may vary based on whatever standards you're working with. If you're using Q5 or BPI, they all have different ratings. But the point is, you want to have a low, the lower the better, leakage of the duct system. So, for an example, if you measure 1200 CFM for airflow, and this will be derived by the data plate on your system. If I have a 3-ton system and it's 400 CFM per ton, that's roughly 1200 CFM. If I pressurize a duct to CFM 25, I will be looking for a leakage rate less than 10%. And this will let me know that the ducts are indeed above whatever standard you're trying to measure, right? And if you don't have the number below 10%, then you need the duct seal. You need the duct seal and then reperform the test, right? Now, what about the duct leakage outdoors? All right, this test is a little bit unique because you have to run this test while the blower door is running. And in both situations, you're going to run a duct leakage tester and a blower door to 25 pascals. And what you're trying to do, you're trying to balance the pressures between the house and the duct system where they won't leak to each other. And my only leakage that's going to occur is going to be outside. All right, so here's a picture of the total leakage test. All right, again, with the total leakage, I'm just looking at the ducts. All right, how bad are they leaking? And one of my reference points is going to be how much percentage of total CFM air handler flow am I leaking? Some energy codes actually look at the duct leakage from a CFM per square foot, and then you'll find out in some energy code requirements. All right, the moral of the story for total duct leakage: how much leakage do I have? Is it acceptable? When I look at a duct leakage outside, I'm looking at the leakage of the ducts, but how much of that leakage is occurring inside the building shell as compared to outside? Let's take a look here. All right, we have our blower door operating and our duct leakage tester operating. And the way this works, whatever the blower door's direction of airflow, either pressurized or depressurized, I have to have the duct leakage tester pushed in the same way. And when I do that, I'm trying to get the pressures to cancel out. And when I get them to cancel out, the house and the ducts are at the same pressure. They can't leak within each other. Then my only leakage that can occur is outside the building shell. All right, and we're able to quantify that and put numbers behind it to see what our energy penalty is. All right, here's how it works. Again, I run a blower door and duct leakage. They need to be going the same direction. So if my blower door is in pressurized mode, my duct leakage tester needs to be in pressurized mode. All right, I need the pressures to cancel out. As I'm moving air through the duct system, if it can't get into the house, it can only leak outside, and I'm going to quantify that. All right, our next duct
Well,
evaluation.
can, and if I can chime in real quick, Bryn,
Yep.
back to the other point, a lot of people forget that under lead energy and atmosphere minimum energy performance, total duct leakage to outdoors is mandatory. You have to do these two tests at the same time. Sometimes we'll see the duct blaster test done and we'll see the blower door test done, and then someone's, did you do them at the same time? No, you got to go back, right? So I'm glad you brought that up because that is required for Energy Star certification. It's required for lead. We need to have that whole number. Or again, like we said at the beginning, do a ducted mini split or mini splits, and then there's nothing to test. So you eliminate that whole concern there. But certainly on existing homes, you're limited, of course, on that. So I just wanted to point that out.
Oh, good call out, Brett. And I'm a duct person, so what's the fun of not testing the duct system? Absolutely. Great call out. All right, so our next procedure is going to be room to room imbalances. Okay, what is that? So this is another procedure that we're going to use. All right, the way this procedure works, I have to have the air handler running. all right, the air handler running or the blower on the furnace running. And when I'm running that blower on the furnace, what I'm looking for is, do I have enough CFM going into the room? And do I have enough CFM going back to the air handler? All right. In all the rooms, that should be balanced with the exception of the kitchen and bathroom. We don't want return air back. So this room is done for bedrooms. And if you see on a picture, if I have an imbalance, that's going to cause some comfort problems, and it can also exaggerate building shell leakage. Okay, so let's discuss the procedure. Now, in a room-to-room air pressure, the air handler or furnace blower is running. And what I'm looking at, I'm going to stand essentially inside the home, and I'm going to measure with reference to the house. I'm physically in the hallway, and I want to take a tube and manometer with the air handler running, and I'm going to throw a tube on each door. All right. And what I'm looking for, I'm getting a pressure differential measurement. And with this pressure differential measurement, if it's excessive, that lets me know I have an imbalance. All right. If it's small, that lets me know that I need to, that I'm okay. But if it's large, then I have a problem. So I'm going to stand, I'm going to compare each of these rooms, and each of these rooms are going to let me know if I have an imbalance. This is important. You may have some customers complain that they become uncomfortable once they close the door. All right. They may have a lack of supply or return air, and we need to identify why. All right. So what we do, we have the air handler running. We're going to take a manometer like the technician in this picture does, and we're going to take a tube and we're going to compare it, that room with reference to the hallway or central part of the home. And what we're looking for, anything over 3 pascals. If it's over 3 pascals, that lets me know that I have an unacceptable pressure differential. All right. I have too much supply, not enough supply, too much return, not enough return. They're unbalanced. Okay. And this will let me know that if I'm unbalanced, I have some issues. Take, for example, I have too much supply situation, as you see on the right part of the screen here. All right. If I have a supply that is positively pressurized in building space and I can't get the air out, eventually what happens, that room will pressurize to the point where air will start to stop to coming out of the register. But when it stops coming out the register, if you need the conditioned air to come out to keep you comfortable, it won't happen. Also, when I positively pressurize that room so much, I now start to get building shell leakage out of that room. All right. So one CFM in, one CFM out. I'm going to pull air, unconditioned air from another location. And now my air handler has to heat up that conditioned air just because I had an imbalance. All right. So these are room to room pressures. Magic number is 3 pascals. Okay. How do you fix it? We fix it by trying to, in most cases, trying to get return back to the air handler. Oftentimes it's a return problem more than a supply. All right. So some of the solutions would be to undercut the door. All right. You would take some of the doorway. All right, but you lose your privacy, not the best solution. You can add jumper ducts. Jumper ducts are located here in the attic. So if you look here, all right, I got a jumper duct right here, and I'm going to communicate these two rooms to get air from one location to another. Now, the jumper duct, if it's going in the attic or crawl space, is going to have to be sealed, properly sized, sealed, and insulated. All right, so I can install a jumper duct. I can install a door grill or wall grill, properly sized, or transfer grill to get air from one location to another. Or my favorite, if possible, is to install a dedicated return. Right. And once I make the repair, I'm going to reperform the test and see if I can get below those 3 pascals. Really great tests, often underutilized to solve comfort problems. All right, let's talk about measuring airflow. All right, measuring airflow. Oftentimes, when you're chasing an airflow problem, the first place I really need to start is the system producing enough airflow for the weighted equipment capacity. All right, so we got a few types here. We got static pressure, we got pressure matching, we got a heat rise where we can use a formula, and we can have direct airflow measurements like you see here with a flow grid. Here are some of the tools that you can use for direct airflow measurement. Now, static pressure, we'll talk about each of these and some of their benefits, but the moral of the story, you want to measure airflow. With duct problems, you can only find out what the problem is if you have the data to support what the duct issue is. Okay. Let's talk about the flow hood. All right, flow hood is purpose. It's a device that's going to capture the CFM. All right, you're going to read CFM directly. All right, it's a calculated because the dimensions of that flow hood are known. All right, so it's based on CFM. through a supply return. And there's two types. A passive flow hood is just that, it's just going to capture it. A power flow hood is actually a little bit more accurate because it has a fan that's going to reduce the pressure, all right, pressure drop of the flow hood. In either case, using these will help you identify problems. Now, how do I use it? Oftentimes, when I'm trying to troubleshoot to fix a comfort problem, I'll first start by doing a load. And when I do a load calculation, I come up with the CFM I need for each room. And when I have that information, I'll measure the CFM coming out of register or grill based on what my load calc says. And if I have some kind of discrepancy, there's my smoking gun. That's the issue. I need to address why the ducts are not delivering up there. Could be a sizing problem. Okay? Now, Brent brought this up earlier. He was talking about some of the different standards. Now, you got LEED, you got Energy Star, you got ResNet, you got ACA, you got BPI, you got all these standards. You have to use whatever your program is going to call for. We're a BPI training organization, so we often use BPI specifications. So this is what you see here on the screen. When working with registered airflows, we like to make sure that the duct systems are within 20%. Some programs are more aggressive. Some say 10%. So again, it depends on what program you're going to work with. All right. The moral of the story, I have to have enough CFM coming out the registers to deliver the BTUs to offset what I'm doing, either heating or cooling. All right. So whatever program you're going to work on, make sure you understand those numbers or targets. All right. Oftentimes, this device is going to be hard to use. All right. This is a flow hood here. All right. Sometimes this may be impractical to use. We may have to switch to this. This is a vane anemometer. All right. What this purpose is, this measures air velocity in feet per minute or meters per second. And what this is done, what it's used for, I can measure the airflow coming out of register or grill. Now, it's a little math that I have to do. This only measures feet per minute, and I have to do the equation to figure out what surface area that I have and if I have the AK ratings on registers or grills. When you use this, a lot of people say they're not accurate. And sometimes it comes to the air. You're supposed to transverse the area of that register or grill. All right, and you come up with an average. Some of the better tools actually come up with the average so you can get an average airflow. And when you do, this is a way for you to get airflow information that you might not be able to use a register or grill. So this is actually, is it less accurate? Yes, but it's still relatively accurate enough to help you evaluate duct systems. Let's talk about static pressure. All right, static pressure is bursting pressure, bursting pressure. Static pressure, I like to call it a proxy measurement. All right, what static pressure is, I am able to measure the bursting pressure of the ductwork. And what that tells me, that gives me an indication of airflow. How static pressure works, if my static pressure is high, my airflow is lower. And if it's high and my airflow is lower, I could get to the point where I can start chipping out on temperature limit. Now, how do you evaluate static pressure? With static pressure, I need to install test ports and I need to measure the pressure differential of the equipment the way it was shipped. When I have a furnace here, notice how I have my manometer measuring after the filter or downstream of the filter and before the evaporator coil. If you look at a four-step furnace, it was shipped without those components. So when I evaluate those two locations, I call that internal external static pressure. And this gives me an indication of airflow. Once it gives me an indication of airflow, I'm able to use this information and come up with a CFM number of total system airflow. This is a furnace. This is an air handler. Now, with an air handler, the coil is integral. It's installed at the factory. All right. So since it's shipped that way, we include it in our static pressure measurements. All right. So since it's shipped that way, and depending on the manufacturer, it may or may not have a filter that you need to account for also. With this measurement, notice how the blower and the AC coil are within the static pressure probes. All right, and I will take this information, and this has a different static pressure requirement because the coil is integral. All right, so this is an air handler. The way we get airflow, manufacturers profile the heat exchanger. What they do, they run a heat exchanger through several flow characteristics, and they're plotting the static pressure. When they plot the static pressure, they give you a way to take that static pressure information and come up with a airflow in CFM. Now, this is great for new equipment, but however, one of the disadvantages is as this equipment starts to foul, or if there's any kind of neglect, this becomes less accurate. So it's more accurate on newer systems. It's a way to get airflow, but just know if the system has been existing for some time and there's any kind of dirt loading, this may not be the best method to get system airflow. When you get to static pressure, if you don't measure external, you can measure supply and return, add the two numbers together, and that will get you your total external static pressure. Yep. All right, the way it works, you're going to fire up your equipment, get your static pressure reading, and you're going to take that reading and compare it to a data plate. All right, here's a visual indication of what happens. At static pressure, if you look at the bottom of the screen here, right here, if you look at the bottom there, notice how at 0.31, I got 1600 CFM. And notice how as static pressure rises, my airflow drops down. So static pressure is an awesome way or a proxy measurement to help you understand what airflow is doing. It lets you know, all right, the higher the static, the lower my airflow through the system. All right. Let's talk about pressure matching. Pressure matching is a way to get airflow, system airflow. And how it works, I'm going to take a duct leakage tester. And when I take that duct leakage tester, first I'm going to run the system and I'm going to get a pressure measurement in a duct system. All right, and my manometer is going to save that pressure measurement. And then I'm going to turn the system off and run my duct leakage tester. And my duct leakage tester is going to increase in flow until it matches the pressure. And when it matches the pressure, it matches how many CFM did it take to get through the duct system to match that pressure. So it's a neat way to get a system airflow by using a duct leakage tester. Now, some of the disadvantages is a little hard to set up, and we often see raters use this, HERS raters use this. They already have to do some type of duct leakage testing. They already have it set up. This is another way for them to get airflow. So just a way to get total system airflow. What about temperature rise? Temperature rise oftentimes unutilized. All right, what temperature rise is when I'm dealing with a combustion appliance, they have a rating plate that specifies the range that the temperatures are supposed to be supply and return. And as an auditor or a technician, we can measure the supply and return and see what the difference between those two numbers are and make a comparison. And when we make that comparison, this lets us know, am I circulating enough air through that furnace and duct system? And that's a temperature rise test. And how it looks, all right, I'm going to put a thermometer in a supply duct. I'm going to put a thermometer in a return duct. And I often want to put these out of the vision of the heat exchanger. In the heating mode, radiant heat energy can affect my temperature reading. So as a result, I want to put it maybe about a foot away. That's where I put mine. And I'm going to subtract the furnace supply from the return. And I'm going to get a number. Now you see the 70 degrees Fahrenheit in this application. What happens, I'm going to take that 70 and I'm going to compare it to the bonnet data plate. Manufacturers produce temperature rise ranges for their equipment. So if my furnace set 35 to 65 temperature rise and I measure a 70, guess what? My bonnet is overheating. It's going to short cycle on high temperature limit. I don't have enough airflow circulating through the system. All right, this is a great way to evaluate really quickly if you have an airflow problem. And you can also use this in formulas to calculate system airflow. All right, excessive temperature rise. All right, low fan output. I got the wrong speed, bad motor bearings. I got low voltage, dirty blower wheel, wrong rotation of belt. Anything that's going to stop the blower wheel from turning fast enough to deliver that airflow. It can also come from restrictions, undersized ducts. That's what we're talking about today. It can also come from some neglect, maybe a dirty filter, dirty coil. Or it can come from a overfired situation. Maybe I have too much gas pressure with the combustion appliance. All right. When it's too low, all right, that can be excessive fan speed, which is wasteful. Duct leakage. Sometimes duct leakage can cause where I have a low temperature rise. And it can also come from underfire. My gas pressure on my appliances or my nozzle pressure for oil isn't high enough, which is also a problem. All right. When the temperature rises too high, it can cause rocking on the temperature limit. Rocking on a temperature limit is when the limit switch that we discussed earlier, all right, opens up and shuts the equipment down. And the limit is manual reset. So when it cools off, it closes back. But my airflow problem is still there, so it opens. And then it cools off and it closes back. When you have a piece of equipment that stops all of a sudden and then comes back on all by itself, could be likely that you're rocking on a temperature limit. And I see novice technicians make a mistake where if a limit switch fails, they'll replace the limit switch but not address the airflow problem. So it's something to look at. Over a long period of time, we can get a damage to the heat exchanger. All right. Remember that crack we talked about, that annealing? All right. If we damage the heat exchanger, that can come from not enough airflow, high temperature rise. If it's too low, that can lead to condensation in exhaust gases, all right, which is acidic. All right, it can damage our exhaust piping for certain appliances, can cause soot buildup, and also lead to customer discomfort, which isn't good either. All right, real popular now is direct flow measurements using a flow plate. All right, this flow plate, the way it works, we're going to take static pressure measurements, and then we're going to remove the air filter and then put in this flow plate. And when we take this flow plate, it's going to take the static pressure measurements we had, and it retains the pressure drop of the filter, and then it measures flow, and then it interpolates what the airflow of the system is. Really awesome tool to get airflow and static pressure really quick. All right, so this is a flow meter. All right, Energy Conservatory makes this tool. It's really awesome, not from a marketing standpoint, but I've even seen utility companies start to specify using this tool because it gives you airflow and static pressure really easy. One of the reasons I like it is that it also gives me a report. I can actually show the customer that they have a duct to equipment problem, and here's the airflow measurement, and here's why I'm saying it. And it has a red, yellow, green hierarchy. I can tell how I'm doing based on some settings that I can change. And those settings can indicate and let me know if my static pressure is high, it can put that in the red. So it's an awesome communication tool to give to your clients. All right. And here's how it looks. This is the TrueFlow grid being installed into a filter grill. All right, we're taking the filter out after we take our measurements and we put the filter grill in, and we're able to calculate airflow and get static pressure. All right, here's another report, same information. We're able to see this and give this to a customer and see exactly what's going on. Now, when we look at the air handler flow, they're generally designed to deliver flow based on their sizes. So if we look at a furnace input, all right, if I have a 100,000 BTU furnace, all right, many manufacturers, if you were to look up several of them, they all kind of land about the 1200 CFM mark. All right, so we know that if we're in heating mode and we have a significant lower level of airflow, that's going to populate red when we start to make these kind of reports. We also have a duct traverse. We used to do this quite often before we started using flow plates. The duct traverse, we're going to drill test ports inside of a duct system, maybe a supply return, and we're going to use a hot wire or pedostatic tube, and we're going to basically take velocity measurements in the duct, right? If we take velocity measurements in the duct based off this traverse, we can take the average velocity of the traverse, entire traverse we do, multiply that by the area of the duct, and we can calculate CFM. Really accurate, however, it was pretty time consuming. You still see this as a required step in commercial test and balancing, but with flow plates becoming more popular, you see this maybe not as quick as a solution, but it's definitely still accurate and something you should consider. All right. Won't spend a ton of time on electrical, but you can also identify some electrical airflow issues by measuring amps. Okay, if I have low amp draw compared to what the motor says, if you're qualified to take the electrical readings, that's also an indication that you may have something. So this is another measurement that can be taken to help you pinpoint exactly what's going on. Now, let's talk about assessing the ductwork. So we covered the problems. Let's look at actually evaluating it. All right. First things first, you need to have a client interview. All right. Did the customer tell you what was going on? Did they identify those uncomfortable areas? Brett mentioned it during the introduction. What about noise? If I have a duct system that's really tight, oftentimes it's really loud. I've been in some customers' homes Or when the duct system is the air handler is on and air is coming out of the duct system, they have to turn the TV up just to hear the TV, right? So that lets you know that you have a problem. So you're going to ask about uncomfortable rooms, excessive noise, and then also about short cycling. If you see that kind of thing, obviously you want to pay attention to it. And then do a physical inspection. We see here that a plumber was kind enough to cut some plumbing work to a return. That was nice of them. Yeah. All right. In this situation, we call this Bluetooth ducting. All right. Sometimes it's good old fashioned evaluation of the duct system to see what's going on. Oftentimes, the problems are pretty apparent. All right. So remember, look for things like this, but you also want to determine with your tests what are the things you can identify with those duct systems. All right. All right. Here's the big six. All right. Duct leakage. All right. Room to room pressure, static pressure, temperature rise and blower, and not mention is direct airflow measurements. If we use these tools, we can evaluate any duct system and any problem. They're going to fall into these issues. All right. And with that, we'll wrap it up. What we're going to do, you're going to look at your duct system and write down possible problems. Oftentimes, I like to make a drawing. I like to make a drawing, make a blueprint, and identify where the duct issues are. So that way I have a reference point when I make repairs to see exactly if I changed it. All right. The goal is to test in and test out and make improvements. All right. You want to determine what alterations you need to make. Sometimes it's a ductwork modification. Oftentimes it could be the equipment is too large, and you'll be able to decipher that with the testing. And then you're going to educate your customers on the best strategies. And with that, Brett, I'll pitch it back to you.
Yeah, thanks, Bryn. We got a lot of questions coming in here. Do you have time for a little bit to stick around and get to those questions?
Go for it.
Yeah, great. And just everybody who's here, I know some questions are in the chat. I'll probably miss them there, so just get them over into the Q&A, and then that way I don't miss them. But I think there was just one of the first thoughts was just the clarity again on the two duct leakage tests. If I understand correct, and you can elaborate again, was there's that pressure pan test, which is really, if I understand right, looking at the performance of the design of the system. If it's too small, is the problem. And then the other one, the duct blaster, really was actually looking at duct leakage. Am I saying that correct? Can you just elaborate a little bit more?
Sure. The pressure pan test, the ducts are connected to the building shell. All right. They should be at the same temperature and pressure as a building shell when they're in service. If they're outside the thermal pressure boundary, they should still be at the pressure inside the building shell. So what the pressure pan test does, it helps you determine is the shell leaking through the duct system. All right, so pressure pan, first things first, the blower door has to be running. When the blower door is running, it makes a 50 pascals test pressure difference. And I'm going to use that reference point to check across the thermal pressure boundary, that drywall. And it's letting me know, is the ducts leaking through the building shell? Do I have some type of communication? I want the shell and the duct system to be pretty close to zero. If I have something significantly greater, like close to 50, that means the ducts are relatively connected to outside. So that's that part of it. The second part you hit right on the head. The duct leakage purpose is to quantify duct leakage. That's the purpose of that tool. What is the leakage rate of the duct system? All right, so just like we get a leakage rate on the blower door, same principle. All right, what is the leakage rate of the duct system? So they're both evaluating duct leakage, but they have separate meanings. The pressure pan is evaluating duct leakage to the shell. The duct leakage tester is evaluating total duct leakage.
As we are watching those questions come in, just a quick reminder before we officially wrap up and switch to Q&A is that yes, this session is being recorded and it will be posted on our YouTube channel in the next couple days. So you can check back there in a couple days or go there right now, click subscribe, ring the notification bell, and you'll get an instant update when it is available. For those of you here, the entire CU hour, check your spam at certs@gutenbergcerts.com. And you'll receive your certificate. It'll go up on your account. You'll have it up there as long as you've been here the entire CU hour. For those of you watching this in the future in the recording, just make sure to take your quiz with an 80% passing rate. And again, as those questions are coming in, we're going to get to them. A huge thanks to our board of directors, our executive director, Jose Reina. our all of our volunteers and all of our members, nearly 500 who support our work. We're almost there. We hope you can help us reach our 500 member goal today. If you haven't yet, I'll send some more information in the chat. And of course, our sponsors who are making products that are going to help you decarbonize, live more sustainable, save on your utility bills. Ream, Timber HP, Architectural Resource for Design, Serve, Panasonic, all of them who support our mission and allow us to do these kinds of things. Bryn, sound. So you talked about kind of going in at the end there and asking a question. Hey, right. And any good evaluator is hopefully going to ask the homeowners or the tenants, what's going on? What's your concerns? Let's understand those. You might ask, is this loud? But are you going to use any actual evaluation tools? Like with lead, we actually have to evaluate the sound. We have to walk into that room at 35 decibels to 40 decibels, depending on the room. Are you actually using science, or is it more just, is it too loud, or is it a little bit of both with how you're doing it?
So lead is definitely best practice.
Mhm.
You should measure them with the decibel meter. Oftentimes, with the other, I'll say standards, once you reconcile the duct size, the sound
Yeah.
kind of takes care of itself. I think testing sound is definitely best practice, but the sound comes from undersized duct systems.
Yeah. Another question was on the general static pressure and fan speed chart you were referencing. And if you wanted to pull that back up, you should be able to share again. But they're saying it looked like the equipment would have to have been rated at zero point 0.3 IWC. So even if it's zero point 0.5 of IWC, would it be too much pressure? So I think they're asking the question from the context of what the system is rated versus what you were saying, if that makes sense.
Let me pull it up. I think they're asking about this one here.
And you're not sharing anymore if you just want to turn it. There you go.
Okay. All right. Let's discuss the rating. So furnaces are rated and tested. They're tested at zero
Mhm.
point 0.5 inches of water column. All right. The test rating pressure, that's what they're rated at. Oftentimes, when you put a indoor coil for a heat pump or evaporator coil, oftentimes the duct procedures have you design static for zero point 0.7. All right, so the zero point 0.5 isn't a number
Mhm.
that is, it's what the furnaces are tested at. Once you start getting into the zero point 0.9s and one inches of water column above zero point 0.8, that's when you start to have
Mhm.
equipment problems with the new modulating equipment. So that's one
Mhm.
key clarification. When you look at an air handlers, many of them are rated at zero point 0.8. The coils are integral. All right, so the duct modifications that you're going to do are going to impact that total thermostatic pressure. So we don't necessarily strive for the zero point 0.5. That's the test pressure for a gas furnace. We're looking to design it where the static pressure is modest. In some cases, it might be zero point 0.7 because we're adding an evaporator. We have to sometimes decide it at zero point 0.7 just so we have enough static pressure available to push the airflow throughout the duct system. If you look
Mhm.
at tools like Energy Conservatory, oftentimes they'll default the default settings, unless you change them, are often I forget either zero point 0.7 or zero point 0.8, or they'll start to consider that high. All right, so
Mhm.
that's a test pressure. That's what the furnace is tested at.
And speaking of static pressure, it was interesting because I saw you testing after the filter. Now, of course, one of the things that we look at with static pressure, and this is extra lead credit in especially in version 4.1, and just a general best practice, of course, if we want to be healthier in our homes, we want to have those higher MERV systems, right? And so if you're testing after the filter and you're trying to determine if someone used a thicker filter or a thinner filter with a higher rating, and that's a drag on the system. I just had a project come back and they tested and they broke out in the visuals, very nice,
Mhm.
where each static pressure number was 1 plus 2 plus 3, where those numbers were coming from. And it showed me the filter was responsible for this, right? And they told me that. So if you're testing after the filter, do you lose that or is that somehow still in there?
So it depends on what you're testing static pressure for. So the context of this presentation, we were using it to get a reference point so that we can look up a
Yeah.
chart and get airflow.
Yeah.
The external static pressure still accommodates the pressure of the filter. So you're measuring external
Mm.
static pressure if you make a filter replacement. So for example, where you're headed, a
Mm.
1 inch pleated filter is really restrictive. I've
Right.
seen some articles that it had the same pressure drop as a piece of cardboard.
Yeah.
And it might be best to upsize that filter to increase the surface area so that you can reduce your static.
Mm.
So you would measure across the filter if you're trying to evaluate that. So maybe a part two we should think about in the future after we get our air handler measurement, our airflow, maybe going back and making modifications because you can actually take static pressure and look at
Mm.
certain parts of the system and see where the problem physically is. Now, when you look at MERV, a higher MERV rating, that is a more restrictive filter. Before you make that adjustment, Brett, you will have to verify that the duct system can handle that more restrictive filter.
Yeah, that makes sense. Do you still have some time for some more questions?
Sure, go for it.
Yeah. So I think in general, people in existing homes, they're looking at, okay, I've got this bonus room, I'm upstairs, and it's always 3, 4, 5. Someone here even said 10 degrees different than the thermostat, right? And a lot of these ducts are buried behind the wall, they're panned in the joists. And so you clearly presented, I think, some solutions, but can you just, for anyone who might have missed it, thinking, oh, I gotta, if I can't afford to tear out all my drywall, rebuild all these pan joists, really, what are your options here in these older homes?
So it depends on the problem. If I'm troubleshooting, again, if I'm chasing an airflow problem, I start from a manual J heat loss, heat gain calculation.
Yeah.
I'll get the BTU requirement of the structure, and then that's going to tell me the airflow is required. So it depends on what problem I'm chasing, Brett. Is it a airflow problem? Do I have the proper CFM that I designed, and is that am I physically measuring that? If those are not close and not reconciled, that's really where I need to start. And if I have that issue, I need to then go look at the duct size. I need to go to the air handler and look up the branch and
Mhm.
see if it's big enough to accommodate. If it's
Mhm.
not, then you're really restricted to what you do unless you add another supply or make that one larger. The other test, if my
Mhm.
airflow is pretty close, all right, is it a shell problem? All right, is it a
Yeah.
shell problem? Am I leaking through the shell? Do I have poor insulation where I maybe have a shell related problem? I have too much
Yeah.
load for that airflow that's coming out. So I have to look at that.
Yeah.
Is it a duct leakage problem? All right, so I have to look at that. So it just depends
Mhm.
on what problem you're chasing, and that's why we cover
Right.
those six different parameters.
And I think that just goes to show that the point here, and it's getting into this next question, is in an existing home, you've got to get your team in, someone who's BPI, someone who understands these things, who you're training a lot of people out there.
Mhm.
So that's really cool to see all that and people understanding this. So I think the point is get someone who knows what they're doing in to evaluate it. It's all subjective. On a new construction, hire someone in the design stage to guide you, right? And then test it mid-construction. Someone pointed out to me, hey, Brett, on LEED, you can do duct leakage testing at mid-construction. And it's absolutely true. You can do that. The problem with that is we find most HVAC is just not ready to do, and we're
Sure.
finding that more and more. So I'm just saying thank you to the person who mentioned that to me in the chat. But have a professional involved in the design through construction, testing, inspection, and evaluation, like Bryn's team here. So the question is that I'm getting to is how much is this going to cost me, right? If I bring someone in, new construction, existing maybe, to look at this more holistically, like you're recommending, what is that going to cost? And are you seeing resources to help fund that, especially for some income qualified projects?
Sure. It depends on the level of audit. So
Yeah.
BPI trained auditors do it all the time. HERS raters, we mentioned those. Those that's a service that construction companies can work with. I
Yeah.
guess the true question would be, Brett, what would it cost you if you don't get it done? That's really the cost up front is a minimum compared to a lifetime of that house having high bills because they have a poor duct system.
Yeah. That's a fair cost benefit analysis, right? Do it.
Sure, absolutely. Yep.
So the other question that came in was if replacing ducts at the time of renovation, exposed ducts versus boxed in. So exposed ducts not insulated in living space, an advantage due to more radiative surface in addition to conditioning via airflow. Does that question make sense?
A little bit. The ducks are better inside the conditioned space. I think that's where they're after. Yeah. If I had a choice to put ducks, I would put them inside the thermal pressure boundary.
Yeah. And what do you for pan joist replacement, if those can if you can get to that, are those typically things that are getting recommended when you can get to those joists?
Those are hard to cope with. Matter of fact,
Yeah.
I applaud the state energy codes that actually remove those
Yeah.
from the construction. So pan joists are usually when we measure static pressure profile across the system, breadth the return is always high,
Yeah.
just because the joist space are tight. And you can have leakage paths from the building shell that you may not be aware of. So, if
Yeah.
possible, we like to seal those, maybe using a solution like AeroSeal, but
Yeah.
they are generally tight when you measure the return system back. So oftentimes, what we'll do when we replace a system, a heat pump or a furnace, we'll upsize the return to get more airflow to the air handler, but the pan joists are a problem in this country.
Mhm. And so the other question is like in your inspection process, have you seen or needed to consider like an internal? I think the question that they're asking here is sending like a little video capturing something you can thread into the ductwork and see what is going on in there. Have you done anything like that before?
Yeah, if I've sent in a borescope into
Borescope.
duct systems, yeah, but the testing protocols that we talked about that led me to do that because I wasn't getting an appropriate airflow. I found soccer balls, small soccer balls inside ductwork. I found GI Joes and transformers and all of that kind of stuff inside duct system. You
Yeah.
stick your camera in and you see that, and you obviously got a problem. So I let the data drive me to that physical inspection.
Yeah, you saw that you need to. And then I think, and this might be a whole other topic, and we have other recordings on it. I'm sure you all do. Where does, at a high level, humidity come into play in this conversation here?
It comes in a lot,
Yeah.
especially with duct leakage. If I have duct leakage inside of an attic and I'm in a hot, humid climate, or in the summertime, and I have that return duct leakage, is going to pull in that hot, humid air. And if I can overwhelm the system where I can't manage it, and then you're throwing on that problem on top of the air conditioner probably being oversized and they couldn't manage the moisture in the first place. Moisture is definitely a consideration.
Yeah. That is all I see as far as those specific questions. We'll send out an update with any of the other ones we missed, Bryn. But in the meantime, I guess the question is where can people go to learn more about what you're doing, about learning more if they're professionals and they want to get engaged and understand this, or if they're other professionals who aren't in HVAC and they're like, hey, I need help in my home, I need help with my projects. Where can they go to contact you to learn more?
Sure. My direct email, I'll put it in the chat here. It's brand at HVAC Train. They can reach out to me directly. If you want to visit our website, it's hvactrain.com. And we're a full service technical training, technical trades training organization. A big thing we do is teach building science, and we're a BPI test center. We travel, we're based out of Michigan, but we travel all over the country and deliver these seminars and stuff like that. And then if they want to follow a lot of the stuff that we're doing, they can follow me on LinkedIn. That is at the Air Doctor on LinkedIn.
Yeah, absolutely. Connect with Bryn on LinkedIn if you haven't yet. So much great stuff going on, and I'm always learning something new. Yeah. All right, Bryn, thank you so much. And we will catch you next time, and we'll see the rest of you next week. So be well, take care. Goodbye.
Take care.